Hello friends, welcome back to my channel Chemistry Unplugged. Today we will learn stereoisomerism in coordination compounds. We will start with geometrical isomerism. I will explain you it with examples, and I am also giving you some tricks to calculate number of geometrical isomers. Stereoisomerism can be divided into two categories. What is stereoisomerism? Means number of atoms are equal and their bonding is also same in the isomers, but their arrangement in space is different. It can be divided into two categories: is geometrical isomerism and optical isomerism. First we will take geometrical isomerism. It is generally studied in coordination compounds having coordination number 4 and 6. The geometry of coordination number 4 compounds is tetrahedral and square planar. This is the tetrahedral geometry and it is square planar. Okay, and the geometry of coordination number 6 compound is octahedral. So first we will learn what is geometrical isomerism. Geometrical isomerism means ligands occupy different positions around central metal atom. For example, in this we have two type of ligands, A and B. If ligands A are adjacent to each other, okay, and B are adjacent to each other, means this position is cis, and the angle between same type of ligands is 90 degree. Okay, and if these ligands, same type of ligands, are opposite to each other, this situation is known as trans, and the angle between the two ligands is 180 degree. Coordination compounds having square planar geometry shows geometrical isomerism, but tetrahedral complexes do not show geometrical isomerism. Why? Because all the four ligands are equidistant to one another, means the distance between two ligands is same. For example, this is the tetrahedral geometry and we have this ligand is of different type, and if we place it at the top of the tetrahedral complex, but if we change its position, these all positions are similar to each other. These all positions are similar because this is a tetrahedra and the distance between these two bonds is equal. Okay, but in case of square planar complexes, this distance and this distance is different. So geometrical isomerism is not possible in tetrahedral complexes. So first is geometrical isomerism in square planar complexes. Ma4 type. M is central metal atom and A is ligands. When all the ligands are of same type means all these positions are same in nature. So there is no geometrical isomerism is possible in this case. All the ligands are same in nature, so there is no geometrical isomerism. Next is Ma3B type. 3 ligands are same and one is different. So suppose this B occupies this position, and if we change its position from this to this, and then from this to this, and then from this to this, but all these positions are same, there is no change from this position to this positions. All these vertices of this square planar complex are same in nature, so there is no change in this geometry of this complex and this. So geometrical isomerism is also not possible in Ma3B type. Then we have Ma2B2. So next type is Ma2B2. We can also write down it as MAABB. So now we have a trick to identify number of isomers. So first write down A in one bracket and B in one bracket. Keep it at it as same as it is written here. So what is the mean of this bracket? Means this A ligand is trans to this A ligand and this B ligand is trans to this B ligand. Okay, so A is trans to A and B is trans to B, and this position is known as trans. Next, one possible combination is A can combine with B, this B, and this A can combine with this B. So A, B. So another possible arrangement can be A can be trans to B and next second A can be trans to second B. So in this type of position, these two same type of ligands are adjacent to each other and these two are adjacent to each other. So this position is known as cis. Okay. For example, we have PtCl2 NH3 whole twice. So suppose this is Pt is as M, Cl2 is AA and NH3 can be write down as BB. So what is the first possible combination? That MAA. Okay, so AA means Cl is trans to each other and NH3 are trans to each other. So this position is known as trans. Okay, and in next Cl AB means Cl NH3 are trans to each other and this Cl NH3 are trans to each other. This position is known as cis and this is known as trans. So this is transplatin and this is cisplatin. Cisplatin is an anti-cancer drug but transplatin is not. Other examples of this type is PtCl2, Py means pyridinium whole twice and PdNO2 whole twice, NH3 whole twice. Next type is Ma2BC. So we can write down it as MAABC. So first possible combination is MAA. We will write down it as it is MAA. Then what is left? BC. So MAABC means AA trans to each other and BC are trans to each other. Okay, this type of geometry. Next possible combination is MAB and AC. Okay, MABAC. So one A is trans to B and another A is trans to C. Okay, next type is Mabcd. We have 4 different type of ligands. So first possible combination, in first possible combination we will write it as it is, means Mabcd. AB in one bracket and CD in another. So A and B are trans to each other and C and D are trans to each other. Next possible, now we have AB in one combination. Next we will take this A with C. So AC, what is left? BD. So BD in another bracket means A and C are trans to each other and B and D are trans to each other. So this type of combination is possible. This type of geometry is possible in this case. Now what is left? A is combined with B in this geometry and A is combined with or trans with C in this geometry. So what is left? A can combine with D. Okay, so AD, so AD and AD are trans to each other and BC, what is left? BC are trans to each other. So in this type of complex MABCD, 3 possible isomers. We have an example here, PtBrCl NH3Py. First is A is, suppose this is A is trans to B, Cl. Br is trans to Cl. In next, A is trans to C. C is NH3. Br is trans to NH3. In next combination, A is trans to pyridine and Br is trans to this Py. So these are three possible isomers. Next type is MAA whole twice, means where AA is a bidentate ligand. So we have two bidentate ligand. This is so in this type of complex there is no geometrical isomerism is possible because these two ligands, these two bidentate ligands are of same type. So we cannot change their positions. For example, in case of PTEN whole twice plus, so there is no geometrical isomerism is possible. But if the bidentate ligands are unsymmetrical in nature, for example, we have diglycinato-platinum. In this case, this glycinate ligand has two sides. One donor is NH2 and another donor is oxygen atom. So it can align in two ways. One possible way is that one NH2 and oxygen atom are trans to each other. Okay, one NH2 of one glycinate group is trans to oxygen atom of another glycinate ligand, and this type of geometry is cis. Next possible is that one NH2, the NH2 of glycinate group is trans to NH2 of another glycinate ligand. Okay, so or you may say that oxygen atom of one glycinate is trans to oxygen atom of another glycinate. So this type of arrangement is trans. So geometrical isomerism is possible for bidentate ligands when it is unsymmetrical in nature. Geometrical isomerism in octahedral complexes which have coordination number 6. Okay, first is Ma6, means all the 6 ligands are of same type. So there is no geometrical isomerism possible. Next is second type is Ma5b. B occupies one of the vertices of octahedron. So if we change its position, there is no change in the geometry. Geometrical isomerism is also not possible in Ma5b type of complexes. Next is Ma4b2. We can write down it as MAAA 4 times A and BB. Now we will apply our trick first, that we will place these two A ligands in one bracket, these two in one another, and these two BB ligands in third bracket. Means these two A ligands are trans to each other, and these two are trans to each other, and these two B ligands are trans to each other. So this type of trans because two same type of ligands are trans to each other. Next possible combination is that this A can combine with one of the B ligand. Okay, so what is the possibility? MAA, we keep it as it is, MAA, and one A combined with one B ligand and one A combined with another B ligand. So it has this type of geometry. A is trans to A and A are trans to each other. This A is trans to B and this A is trans to this B ligand. So this type of geometry is cis when this, suppose we have this as triangle, and in this triangle we have same type of ligands, and in this triangle we have two same type of ligands, so they are adjacent to each other. So this type of geometry is cis. We can also arrange it in another way, that but these two geometries are same. Okay, there is no change in geometry. these are two vertices of an octahedron. These are also two adjacent vertices of octahedron. For example, tetraamine dichlorochromium third. Fourth type is Ma3B3. We can also write down it as MAAABBB. So now we will combine this. So first is MAA, 2A in one bracket, AB and BB. So what is its structure? These 2A are trans to each other, A and B are trans to each other, and these 2B are trans to each other. Now next, what is the possible combination that A can combine with B? All 3A can combine with these 3B. So what is MAAAB, AB, AB? And this type of geometry is trans or mer. This type of geometry is cis or fec. Here we are using new terms mer and fis. Mer means when same type of ligands occupy one plane of octahedron. These three are in one plane. And in phase means same type of ligands occupy one face of the octahedron. These are in one face of an octahedron, or this is also one face of octahedron, and these all three are in one plane. Similarly, these three are in one plane. So when they are in one plane, this is mer, and when the same type of ligands are present in one face of an octahedron, it is phase. Example, RHCl3 So these are two possible geometrical isomers of this compound. Next is Mabcdef, means all the 6 ligands are of different type. So what are the possible numbers of geometrical isomers? Place AB in one bracket, and now we will keep it constant. Okay, we will not change AB, we will change other ligands with each other. So first is C is trans to D and E is trans to F. In next, C is trans to E. So what is left? D and F. So D and F are trans to each other. Next, C is trans to F, and D and E are trans to each other. So when we keep AB constant, then C can combine first with D, then E, and then F. So we will follow this pattern. Now we will keep A and C constant, and we will combine B with D, then with E, and then with F. So there is 3 possible isomers when A and C are trans to each other. In next, we will keep A and D constant, and then we will combine B with C, then E, and then F. When 2 ligands are in a bracket, means they are trans to each other. And we will also place them in alphabetical order, means we will always write down B, D, never D and DB. C, B is not correct. We will write down B, C. So you have to follow alphabetical order for this type of trick. Okay. In next, we will keep A, E constant, and then we will combine B with C, then D, and then F. In next, we will keep A and F constant, and we will combine B with C, D, and then E. So in this way, this type of complex can have 15 geometrical isomers. Next type is Maabbcc. So first we will write down it as it is, MAA, BB and CC. Now we will keep AA constant like earlier example. So AA is constant, then BB and CC. So in next, when A is constant, we can combine B with C. There is only one possibility. In this type, there is no D and E, F. So we can combine B with only C. Now we will keep A and B is constant. First we will keep A and A constant, then A and B. Okay, then when we will take A and B in one bracket, then this A can combine with this B, and this B, this and C are trans to each other. Next possibility, that A and C and B and C. In third, we keep A and C constant. So there is two possibility, but these two are similar. So we will not consider it. There are 5 possible geometrical isomers. One important thing is that we can also identify optical activity. We will discuss in detail about optical isomerism in next video, but I am giving you here a trick that we can also identify optical activity using this trick, that when two same type of ligands in one bracket, there is no optical activity. Means when A and A are in one bracket, or B and B, or C and C in one bracket, there is no optical isomerism. Means it is not possible for this case, not for this type also, and not for this. There is only one possibility, that this isomer, this geometry can have optical isomerism. Next type is MAA. AA means it is a bidentate ligand, BC and DE. So these are the possible combinations using the same trick, but AA cannot be in same bracket, because it is not possible that two donor atoms of a bidentate ligand cannot be trans to each other. So they cannot be placed in one bracket. So for this type of complex, 6 isomers are possible. Next we take an example. In this, first we will denote them by ABCD. So central metal atom by M, A, B, C, C for this bidentate ligand, and we have 2 molecules of H2, therefore we will write down it as D2. So first we will try to combine them. First possible combination is AB. We will keep AB constant first. CC cannot be trans to each other. Okay. So C can combine with, C can be trans to D. So CD. Next possible combination is that AD is constant. Now AD is constant. So B is trans to C and C is trans to D. In next type, we will take AC constant. So B, C is trans to each other, and DD. And another possible combination is that BD are trans to each other and CD are trans to each other. So there are 4 different type of geometrical isomers for this complex. Okay. First is AB, means BR is trans to Cl. B is Cl. Okay. In next type ADR, A means Br is trans to H2. In third type A is Br is trans to one oxygen atom of oxalate. Okay. In next type it is again similar to this, but in this case B means Cl is trans to H2, and in this case Cl is trans to one oxygen atom of oxalate. So if you draw the geometrical isomers using this trick, it is very easy. Otherwise you will get confused. In next example, we have Cr, Cn whole twice, En whole twice plus. So we will again write down it as MAB. So M is central metal atom. We have 2 A type of ligands, CN, and En, ethylene-diamine, is a bidentate ligand and we have two bidentate ligand here. So first MAA and BB. These two B, we are keeping these two B in same bracket because these are the two donor atoms of two different ligands, two different bidentate ligands. We have two bidentate ligands, so they can be trans to each other. For example, in this case, this N belongs to this ethylene diamine group and it is trans to this N which belongs to another ethylene diamine group. So in this case, they can be placed in same bracket. In earlier cases, we have only one bident ligand. Here we have two bident ligands. So we can keep them in one bracket for this example. So another possible combination is that A can combine with this B and another A can combine with another B and two B in same bracket. So there is two possible combinations for this type, and for this we have C and Cn opposite to each other and NN are opposite to each other. So this type of geometry is trans, and for this type, same type of ligands are adjacent to each other, so it is cis. So that's it. Thank you so much for watching my video.